Thank you for being here. It's very nice to be here. I want to acknowledge first the support from Fulbright, the Fulbright Commission, and in particular the Office of Fulbright in Spain. And Victoria Ruiz has been very, very helpful in every aspect of us being here in Spain. And also, I want to acknowledge the hospitality of the Consejo Superior de Investigación Científica. My hosts are in Barcelona, in particular José Luis Pellegrí, and here in Vigo my host was Miguel Gil, so I want to acknowledge that. And finally I want to acknowledge the Instituto Español de Oceanografía and my host Manolo, who introduced me, for their hospitality. And like he said, it's been very stimulating, and hopefully we can start some new investigations here. So today I have one message for you, and the message that I have is that regardless of what you've heard elsewhere, depth and width are important. That's my main message. But I'm talking about semi-enclosed coastal bodies of water, semi-enclosed coastal bodies of water. I don't know what you were thinking about. And when I'm talking about semi-enclosed systems, I refer to different scales. Any scale that you're interested in, for example, the scale of the whole Mediterranean and what happens physically in those systems, or other scales like the scale of the Adriatic or the scale of the Black Sea or the Red Sea, even the scale of the Suez Canal there, or even the scale of the Gibraltar Strait. Or even we can go to smaller scales, like the scale of the estuaries in the peninsula in Spain, like the Ebro. Just to give you a few examples, the Mar Menor, the Guadalquivir estuary, the Guadiana estuary, or the Rias. Any of these are semi-enclosed systems for which the concepts I'm going to be talking about today may apply, okay, to any scale that you're interested in. So what happens in these systems? What do they have in common? They all are, to some degree, forced by the tides, and in such a way that during the ebb stages of the tide, you have profiles of depth versus current strength that look something like this, following the sequence from 1 to 5. That's how the tide progresses during ebb. And you see, what you notice here during ebb is that the profile of the currents is uniformly sheared vertically. That is, the changes in velocity are sort of constant with depth. That's in contrast to what happens during flood. During flood, the profiles are more uniform with depth, and they only change near the bottom. Right? So what we have, when we average these profiles from ebb to flood over a tidal cycle, what do we get? We get seaward flow at the surface and landward flow underneath. So if you go like this and you add some feet motion, you're going to have what my students in the US call the estuarine shuffle. But since we're in the Iberian Peninsula, in southern Spain, they like to call it the flamenco estuarino, because if you add a little motion of the hands, then you have the flamenco estuarino. But we're in Galicia, obviously, right? So in Galicia, you would call it the muñeira estuarina, no? or the muñeira das Rias, if you want. So this is the key aspect of the circulation in semi-enclosed bodies of water that I want to talk about today. And in particular, I'm going to be referring to the density-driven part. So I'm not going to be talking about wind-driven part. That's another talk, okay? So in essence, I'm going to be talking about the tidal flows first and how they might be in semi-enclosed bodies of water across a section. And then after I explain that, I will talk about the residual flows. So two big aspects, tidal flows and then residual flows, okay? So first I start with the tidal flows by illustrating what the tidal flows might look like in a cross-section of the Ems River. The Ems River, as you might know, is at the border between the Netherlands and Germany. And if we look into it a little closer, that's what it looks like. And even closer, that's what it looks like. And I'm going to show you data collected at that transect, that yellow broken line, collected with an acoustic Doppler current profiler, repeating a transect back and forth so that we can identify the tidal flow. So if we put our diving gear and we get in the water of the Ems, and pretend there's no turbidity in the water because it's very, very turbid and you can't really see anything. But let's pretend that we can get in the water and look toward the ocean and see what's happening. This is what the flow looks like. So in red, you have okay, first we have in the vertical axis, we have depth and we have distance across the estuary, and we're looking toward the ocean, okay? And that black line is the bottom bathymetry, so the profile of the bottom. And that blanking area above the black line is the area that you lose, that you can't measure with the acoustic Doppler current profiler. But what this is illustrating is red and blue contours. That's what you're seeing right now, going back and forth, back and forth. So red means that water's coming out of the screen toward you, and blue, water going away from you toward the ocean, so the ebb and flow. So two things that I want you to note from this plot is where is the strongest flow? It's at the surface and right over the deepest part of the cross-section, right, in the deepest channel. And that's because of the effects of bottom friction. And notice how the contours of the flow follow the bathymetry very closely. And that's because of the effects of bottom friction. The second aspect that I want you to notice from this animation is that the phase lag of the currents is such that the changes in the current occur first in the shallow part than over the deep part. You might not notice it very clearly here, but I'll show this picture again in a different way so that you can understand that phase lag. And I'm not going to go into the reasons for why the phase lag is the way it is, because it would take me a while, but I can answer that question at the end if you write it down somewhere else, somewhere there, and I'll answer that question of why is it that the currents change earlier over the shallow parts than in the deep part. So this is very nice animation, beautiful, but to understand the physics of it, we need to go to our friend, Newton's second law, which I've written there in words, that the accelerations on the flow are given by the sum of all forces per unit mass acting on the flow, right? So don't get scared, but the way we express this Newton's second law in symbols is like this. So what are all these symbols? If we start from the left-hand side, we have that the first term is the accelerations at one point in space. Okay. How does the flow change in space? Those subindices in the U represent that I'm talking about tidal flows. Okay. The zero subindex that you see there is that I'm referring to tidal flows. So that's the local accelerations. Then we have the accelerations of the flow produced by gradients, spatial gradients in the flow. So those are called the advective accelerations. How the tidal flow might be stronger, as we saw in the channel, than over the shoal. Those will cause accelerations. And then the next term is the effects of the Earth's rotation, the Coriolis acceleration. Right? So on the left-hand side of this equation, we have the accelerations on the flow. And those are produced by the right-hand side of the equation. The first term on the right-hand side of the equation is caused by the slope in the water elevation. So with the tide, the slope goes like this, right? Up and down. And that's what drives the water in or out of the estuary. So that's the main driving force on the right-hand side of the equation. That's the pressure gradient. Then the other term is the flow produced by density differences along the estuary. Okay, so that's what's called the baroclinic pressure gradient at tidal scales. And the final term is what we call the stress divergence, but it only represents friction, the frictional effect. So if we scale this equation, which I'm not going to do, but if we scale it, we can find out that those terms can be neglected at tidal timescales. That can be neglected, and the baroclinic pressure gradient can be neglected too. So we're left with a beautiful momentum balance, or force per unit mass balance, that looks something like that. The accelerations on the left-hand side are produced by the slope in water elevation and retarded by friction. So this beautiful balance just represents a damped wave, a wave that is damped by friction. So that can be that's a wonderful balance, because we can apply it to different kinds of motions. We can apply it to a spring oscillating. We can apply it to a pendulum that attenuates. And that's the same momentum balance that we can apply to a semi-enclosed basin. okay? A damped wave. So that's a differential equation. We can actually solve that equation because it's a partial differential equation. We can solve it. I'm not going to bore you with how it is solved. It is sunny out there, so I feel well, and I'm not going to bore you with the derivation of how to solve this. It just suffices to say that the solution to this equation depends on several parameters. One is that A sub z, which I didn't explain before, but it's the eddy viscosity, how viscous the water is. It determines how viscous the water is. Another parameter that determines the solution is the frequency of the oscillation. In this case, the wave. We know the frequency of the wave. Another parameter that determines the solution is the cross-sectional area of our estuary. Remember, we're talking about cross-sections in a semi-enclosed basin. So that A is the cross-sectional area. And then the final parameter is the distribution of depth. So we can determine that depth for any arbitrary shape, and we can solve this momentum balance and obtain the tidal flows. The key parameter here, because the three last parameters, the frequency, the cross-sectional area, and the depth, we know from the system where we are. We can prescribe immediately. We know the cross-sectional area, we know the depth distribution, and we know what the main frequency of oscillation is in the system. The only parameter that we don't know very well is that eddy viscosity. But we can regard that eddy viscosity as the dynamic depth of the system. Why do I say that? Because the more viscous the water is, it means that the frictional effects affect more of the water column. The smaller that eddy viscosity is, it means that the frictional effects affect just a small portion of the water column. So the higher the eddy viscosity, the shallower the system, actually. And the smaller the eddy viscosity, the deeper the system will be. So we can regard it as a proxy for a dynamic depth of the system, right? So we can solve that equation, as I said, for any arbitrary depth, and we get the amplitude and phase of the currents. But again, this is a beautiful animation, but to understand the amplitude and phase of the harmonic that we're solving for, we can represent it like this. So this is the amplitude of the tidal currents at that cross-section. And again, where do you have the strongest currents? At the surface and over the deepest part of the cross-section, where friction is the least. Right? That makes sense. Now comes the phase that maybe you weren't able to see before, the phase lags between the shoal and the channel. In this case, red means that the changes of the tidal current occur earlier than where the blue appears. So what it means is that when the tide says change direction to the current, that is, when the slope changes, the current will change. And the one to respond earlier is over the shallow areas, also near the bottom. That's where the currents are weakest. So they have less inertia, so they're able to respond more readily to the call from the tide that says, okay, return. I can explain that a little more at the end if you want. And the greatest lag occurs where the currents are strongest, which is at the surface and over the channel. So this is the way we can understand whether our approach to study the tidal currents is valid or not. So if we compare that theoretical solution to what we observed in the Ems River, again between Germany and the Netherlands, this is the observed tidal current amplitude that we show here. So again, we're looking toward the ocean, and that's the amplitude of the tidal current in centimeters per second. So you can see that the strongest currents get close to 140 centimeters per second near the surface over the deepest part. So those are very strong currents. So that's what we observed on the field with our acoustic Doppler current profiler. And the phase that we observed looks something like that. Red means that the phase changes earlier, the tidal current changes earlier than where the blue is. The blue indicates that the currents change later. And by how much? You see it's around 10 degrees over a 12.4 2 hours, which is 360 degrees. So 10 degrees means 20 minutes. So 20-minute difference between the shallow parts and the deeper part. Okay? So now let's see if our model represents this reasonably well. So we compare the amplitude of the tidal current to the predicted tidal current by the model. And you see qualitatively, it looks pretty good. And also quantitatively, the amplitude of the tidal current is pretty good too. The interesting part here is that we've used a very simple approach, right? That of the damped tidal wave to represent reality, and it does a reasonably good job. The most challenging test is with the phase, and you see also that the phase, both qualitatively and quantitatively, in the analytical model, we have a difference of around 10 degrees also, 10, 12 degrees, between the shoal and the shallow part, between the shoal and the deep part. So that's pretty good. And I have many examples, but I'm not going to show you all the examples that I have. But I have many examples in which these very simple physics can explain the distribution of tidal currents in a cross-section. So we can propose that in general, these, the tidal flow in a semi-enclosed basin, if it's shallow enough, if it's dominated by friction, can be represented by the damped tidal wave. Okay, and since that damped tidal wave depends on the eddy viscosity, we can then say that it matters how deep. So depth matters in this case for tidal currents. One thing that I want you to note, for those of you who are interested in biology and chemistry and geology, also in transport of sediments, is the lateral variations in the currents and the phases. So it won't be enough to go and sample at one location, because you will for sure find different fluxes of material, different distributions of material, whether you're in the channel or over the shoal. And I'm going to come back again to that when I talk about residual flows. So that's a very important message that I want to convey, that one station on a cross-section might not be enough to find out what's going on, right? So now I switch to the residual flow. I've talked about tidal flow. Now I go to what happens to the residual flow. So that's just to remind me that I'm talking about tidally average flows. And as I was explaining before, when you have the interaction of fresh water with salty water, the fresh water is lighter. It's going to tend to go to the ocean at the surface. And underneath, you're going to have inflow. So you have what we called it. How did we call it? The muñeira estuarina. So, okay, so that's very nice. But dynamically, how do we represent it? This is again Newton's second law. But now the overbar represents a tidal average of all the terms in the momentum equation of Newton's second law. And again, on the left-hand side of the equation, we have the accelerations. And on the right-hand side, we have the forces that drive those accelerations, forces per unit mass. And again, on the right-hand side, we have the pressure gradient and friction. We can, through scaling, we can show that the accelerations for this tidally average flow or residual flow, all the accelerations are zero or are very small over time. Right? So we can simplify the momentum balance by that approximation, pressure gradient balanced by friction. This is what was proposed in the study of semi-enclosed basins in the 50s, in 1950s. This is the approach that was used to study them. So you have pressure gradient balanced by friction, right? And the pressure gradient has two flavors. The flavor produced by the slope in water elevation, and the pressure gradient caused by the fact that we have light water interacting with dense water that will tend to cause the muñeira estuarina. Again, we have a differential equation that has an exact solution, and I'm not going to put you asleep with that, with how to get to it, but I'm going to show you the result that looks something like this. And as expected, you have flow going toward the ocean at the surface and flow going to inland at depth, right? And depending on what boundary condition you use at the bottom, this profile might be different, but here with this boundary condition, the flow goes to zero at depth. But that's what was proposed in the 50s, and the question that arises next is, how does the Earth's rotation influence this muñeira estuarina? So schematically, the way it does affect, the way rotation affects this exchange produced by density gradient is that the outflow, if we're looking into the basin, the outflow will be leaning toward the right in the northern hemisphere, toward the right, and the inflow also leaning toward the right in the northern hemisphere. Right? So we have, now we don't have a Muñeira estuarina like this, but we have to add a variation to it. So expressed in symbols is something like this, and in which we have the pressure gradient balanced by Coriolis acceleration. That's what we call a geostrophic balance. So this is a framework that was established by Pritchard in 1956 to study semi-enclosed bodies of water influenced by density gradients. So let's look at an example with data to see how these how real observations of exchange flows look like and whether they resemble the Muñeira estuarina. So we go to the Chesapeake Bay and the James River, which is the southernmost tributary of the Chesapeake Bay. And if we look at a cross-section in the James River, and again, we put our diving gear, we get in the water, and we're going to be looking into the estuary now. From now on, all my representations will be looking into the estuary, okay, with depth versus distance across. So this is what the mean flow looks like. We have depth versus distance across, and the white contours, the white shaded contours, is flow that comes out of the estuary, and my label there is in Spanish. And then the flow going into the estuary at depth. So if you look at this, we have sort of a combination of the effects of the earth rotation and what I call the vertically sheared exchange flow, or the Muñeira estuarina. So it's a combination. It's not exactly a vertically sheared flow, and it has some influence of the earth's rotation. But if we solve analytically that framework, that is pressure gradient and friction, and the geostrophic balance in the transverse direction, what you get is that exchange flow. Inflow in the channel, occupying the entire water column, and outflow over the shoals. So it's laterally sheared. So yet another modality to the Muñeira estuarina. So now we go like this. Right? Well, I understand that in the Muñeira estuarina, you don't move your arms very much. So, but you will allow me to do that here. And I'm sorry, I hope I don't offend anybody by being allowed to do that. Anyway, so we have the laterally sheared exchange flow with this, this dynamic framework. But what caused that to shift from the vertically sheared to laterally sheared? Simply the appearance of lateral variations in bathymetry. A triangular bottom converted the vertically sheared to a laterally sheared exchange flow. So bathymetry is very important here. And you're going to say, well, that triangular shape is not really observed in nature. So if we relax it a little bit, the pattern persists. Inflow in the entire water column, outflow over the shallow part. Does that look like what we observed? Well, you can say, maybe, maybe not. Maybe we're missing part of the dynamics with that framework that was established by Pritchard in the 50s. Right? Maybe we're missing part of the dynamics. So what we do next is to add forces along basin. Before we just had pressure gradient and friction, now we add Coriolis to the along basin momentum balance. And across the basin, we had pressure gradient and Coriolis, so we add the effects of friction. So now we have two differential equations, simultaneous, in which the driving forces are the pressure gradient caused by the slope. We know that the elevation in the river is higher than the elevation in the ocean. That's the slope that drives water going toward the ocean. And then we have the other driving force, which is the horizontal density gradient, in both directions, along the basin and across the basin. So those are the driving forces. Who's going to balance those forces? Who's going to balance? Will it be Coriolis? Will it be friction? Or will it be Coriolis? Who's going to win, Coriolis or friction? How do we characterize that competition between Coriolis and friction? If we compare both of them, we arrive at a non-dimensional number. If we compare friction versus Coriolis, and that's the Ekman number. Yes, and the Ekman number is also a proxy for a depth. If you notice in the denominator, we have depth squared. So the Ekman number is a proxy for depth. What does that mean? If the Ekman number is large, it means that that depth is going to be shallow. So we have dynamically a shallow system when the Ekman number is large. And it means that friction dominates over Coriolis when the Ekman number is large. When the Ekman number is small, it means that Coriolis dominates over friction. So we have dynamically a deep basin. I illustrate this in this cartoon, in which when we have a small Ekman number, the frictional influence will be restricted to a very thin layer near the bottom, very thin, in such a way that the water column is essentially frictionless, no friction. So the balance is geostrophic. We have dynamically a deep basin. And when the Ekman number is large, it means that friction influences the entire water column. So dynamically, we have a shallow basin because friction is influencing the entire water column. Okay, so we can characterize, again, the competition between friction and rotation in terms of the Ekman number, because friction or rotation will balance the pressure gradient that drives the flow. So if we have that pair of equations and we solve them analytically again, and I'm not going to bore you again with how to get the solution, but I'm going to show you the results. We can get the solution in terms of the Ekman number. So for a low Ekman number, and again, we're looking into the basin, depth versus distance across. The white contours represent water coming out of the screen, and the dark orangey reddish contours represent water going away from you into the screen. So for a deep basin, small Ekman number, you have outflow leaning toward the right and inflow also leaning toward the right. So you have a combination of vertically sheared and laterally sheared exchange flow. As friction increases, the outflow tends to branch out in two different sectors of the section, or it tends to branch out, or it tends to be divided in two different branches, with the strongest one being on the right because of Coriolis, and the inflow tending to occupy almost the entire channel. As friction continues to increase, the inflow does occupy the entire water column, and the outflow is segregated into two branches. And when Coriolis is not important anymore, the outflow is almost symmetric over the shallow parts, and the inflow occupies the entire water column. Right? So we can see the progression. As friction increases, the exchange flow changes from being like this. The Muñeira modality changes from being like this to being like this. Or said in a different way, as Coriolis increases, it changes from being like this to being like this. Right? So the next logical question is, okay, that's very nice, but how about width? Well, the main message here then is that depth does matter. So again, the next logical question is, what about width? Is width important? How will this solution change if we look at different width of the basin? So one way of looking at it is, if we take the width of the basin, given by that capital B, and compare it to the internal radius of deformation, that's the scale over which the effects of rotation are appreciable. That's the internal radius of deformation. So we can arrive at another non-dimensional number by comparing these two, the width of the basin, the geographic width or the geometric width of the basin, versus the internal radius of deformation. In this case, if we divide the width to the internal radius of deformation, what would you say we have? A little bit larger than 1, right? It doesn't get to 2, but it's a little larger than 1. Let's say 1.5 maybe. So that's just to give you an example. So when this is called the Kelvin number, that's another non-dimensional number. We're comparing the width of the basin to the internal radius of deformation. So when the Kelvin number is 4, you can imagine that that's going to be a dynamically wide basin, right? You're going to have 4 internal radius of deformation in the basin. So we can generate solutions for the same dynamics in terms of the Kelvin number and the Ekman number. So if we look at solutions in terms of the Kelvin number for a small Ekman number, so these are all small Ekman numbers, dynamically deep basins, you see the difference. So width matters now, because when the system is wide, the exchange flow will be laterally segregated. And as the system becomes narrower and narrower, the exchange flow will be more vertically segregated, vertically sheared, right? So to put this into context, you can think of the one with the wide basins. This can be in the Adriatic, the exchange flow in the Adriatic being laterally segregated, or it could be the whole Mediterranean, a cross-section throughout the Mediterranean. That's to put these results in the context of what scales are we talking about. Then if we go to relatively and these are deep basins, right? If we go to relatively shallower basins with a medium Ekman number, so you see also the distinction between the wide basin, in which the outflow is clearly segregated toward the right, versus the narrow basin, in which the outflow is almost symmetric against the center of the channel. So we can put this into the context of the exchange in the Gibraltar Strait would fall right around that area in the parameter space of the Kelvin and Ekman number. And the RIAs, when they're driven by density gradients, they might fall into that part of the parameter space, for example. And then when we go to dynamically shallow basins, the exchange will be laterally sheared. It doesn't matter how wide. Then for shallow basins, according to this theory, width is not important. And we can put, in general, estuaries around that part in the parameter space. Keep in mind that I've written these words in one location, but these systems vary in space and time in such a way that they will have maybe an ellipse of variability in the parameter space of width, dynamic width versus dynamic depth. Yeah, so this is nice, but recently, well, up to now we have these dynamics, right? Pressure gradient being balanced by either friction or rotation, or both, but no other terms in the momentum equation. Recently, there have been some studies that have proposed that the advective terms, and those that are related to the gradients in the tidal flows, produce net flows also, and that force is similar to that produced by the pressure gradient. So they can be important. So then we can use another non-dimensional term. We've already used the comparison of friction versus rotation in terms of the Ekman number, but we can compare now rotation and advective accelerations, or rather advective acceleration versus rotation, and that's called the Rossby number. So the Rossby number can be regarded also as a dynamic width. If you see it, the width appears in the denominator here, so that's a dynamic width. So it's another way of looking at the width of the basin, but taking into account nonlinear effects, the advective accelerations. So to do that, we cannot do that analytically unless you're a math whiz and want to spend several months in the problem. So we've done it numerically with a numerical model, and under a triangular cross-section, over a triangular cross-section. And I'm showing you here different results. I'm going to show you different results in terms of the parameter space. In the x-axis, I have width, dynamic width, or Rossby number, and dynamic depth, the Ekman number, in the y-axis. So for a dynamically wide basin, we have these different exchange flow patterns for different dynamic widths. So for shallow water, if you look at the upper left, for a dynamically shallow basin and wide, the exchange flow would be laterally sheared. This is consistent with what the linear results showed. And then to the lower left corner, dynamically wide and deep basins, you have a laterally segregated exchange flow and some vertically segregation also, but a lot of lateral segregation. Again, these results are consistent with the linear theory. Also for intermediate Rossby numbers, or intermediate dynamic width, not too wide, not too narrow, we have for shallow systems, which is in the upper part, laterally sheared exchange flow, and for deep basins, you have vertically sheared exchange flow. Once again, this is consistent with the linear theory. And then for narrow basins, here it doesn't matter how deep it is, the exchange flow, considering advective accelerations, the exchange flow will be vertically sheared. Okay, so the only difference here in this parameter space between linear and nonlinear theory is in that pattern. Linear theory predicts for shallow and narrow basins, predicts laterally sheared exchange flow. But the inclusion of advective accelerations will make the Muñeira estuarina to be danced from this to be danced like this. That's what the advective accelerations cause, vertically sheared exchange flow. So as you can see, it's very decent or very reasonable to express the dynamics linearly. If we are talking about shallow and narrow basins, then we need to include the effects, the advective acceleration. Okay? So the main message here is that width and depth matter. Finally, most recently, it has been shown that part of the frictional term, which is the rightmost term in the momentum equation, may have two components, two contributions, one produced by the mean properties and one produced by the covariance between the eddy viscosity and the vertical shear in the tidal flows. So this is a mean component and a tidal component. So the new part is the rightmost that I show here. And dynamically, what does that mean? Or rather, conceptually, what does that mean? So what that means is that that term, the new term that people are saying, well, we need to look at this term more carefully, is the fact that these two profiles show the mixing or the eddy viscosity, which represents mixing, during flood, which is the broken line, and during ebb, which is the continuous line. So you can clearly see that there's much more mixing during flood than during ebb. So this is called tidal asymmetry in mixing. The tidal asymmetry in mixing will distort the tidal profiles in such a way that during flood, the profile with a uniform friction would be the broken line, but with the eddy viscosity shown by the dotted line, the orange dotted line, is the continuous red line. The continuous red line is the profile that you would expect to observe during flood. As I showed at the beginning, a very weak shear in the vertical, and the shear, that is the gradients in the vertical, are restricted to near the bottom. That's in contrast to what happens during ebb, in which the broken line would be when the mixing is uniform throughout the water column, but when the mixing is weaker than during flood and restricted to the profile that you see there, then the profile would be sort of uniformly sheared in the water column. So when you average these two profiles, the two continuous red profiles, when you average them out, what do you see? That near the surface, you're going to have seaward flow, and near the bottom, you're going to have landward flow. So this is supposedly a new mechanism that modifies the Muñeira estuarina, and it's reinforcing it. Yeah, so to do this, to study this, we all again used a numerical model and solve a generic shape, a generic basin, solve it over a generic basin with a triangular cross-section as shown there. And I'm comparing there the results of the flow produced by the advective terms, the nonlinear terms that I showed before, and the flow produced by the asymmetries in tidal mixing, which is on the right. Okay, so for completeness, I show you the flow produced by the river, which is seaward everywhere throughout the section, like an open channel flow. And then the flow produced by the density gradients, as we would expect, outflow at the surface, inflow at depth. So if we add all these contributions, what we get is outflow at the surface, inflow at depth, adding directly those four contributions, okay? Which compares very well if we just average the output of the numerical model, the flows obtained from the numerical model. If we just average them, you can see that they're very similar, which tells us that the method is self-consistent. But the main part that I want to illustrate here is in the middle panels. The two middle panels, the advective flow, the flow produced by the advective accelerations, and the flow produced by the tidal asymmetries in mixing. So what happens there is that if you look at the channel, you have inflow in the channel for the advective and outflow in the channel for the tidal asymmetries, and the opposite over the shoals. So what we're proposing, and this is sort of an incipient research topic, what we're proposing is that the advective accelerations are being canceled out by the tidal asymmetries in mixing. So these two new mechanisms that people have concentrated on in the last 5 years or so might be canceling out each other. And we might go back to what Pritchard suggested in the 50s, well, with a little modifications that I showed, the linear dynamics that I showed. So the linear dynamics that I showed is something like this. So we need to do more research about this, whether the tidal asymmetries are canceled out effectively by the advective accelerations. And if that's the case, we can go back to this sort of parameter space in the Ekman number and the Kelvin number, in which we could place our favorite system in this context, like I've done there. And for example, the illustration that I showed on the exchange flows in the James River would fall somewhere in the parameter space there. Right? So you can choose your system and put it in the context of this parameter space of the Ekman number and the Kelvin number. So another very important point that I want to make, and which I mentioned it when I talked about the tidal flows, is the lateral variations in the exchange flows. So again, if you go out and measure your zooplankton distribution or your phytoplankton distribution or any suspended or dissolved matter in the channel, you might find something completely different than what you would find in the over the shoal. So I think that that's very important. That needs to be taken into account to get a better idea of whether there's an export or an import of whatever we're studying. Yeah. So in essence, the main message I repeated is that width and depth matter. And that's what we need to consider when we look at semi-enclosed bodies of water. So with that thought, I conclude my presentation.